Welcome to Maths for All. I'm Aisling Flynn. This is Higher Level and this is Statistics. We're doing the Central Limit Theorem. Okay, so population and sample distributions. Okay, so we've seen population distributions before. We've seen normal distributions. We've seen skewed left and skewed right. Okay, distributions. Now we're looking at what are called sample distributions. So if you take lots and lots and lots of samples from a population and calculate their means, okay, what you'll find is that when you get an average of all those means, it should be something like the population mean. Okay, but if you put them into a histogram and a distribution, you will find, yes, that the distribution will be centered around the population mean. So what are we saying here? The mean of the sampling distribution is the same as the mean of the population, and also the standard deviation of the sampling distribution reduces as the size of the samples taken are increased. So let's look at a picture. This is taken from your textbook. I think it explains it well. Okay, so firstly let's look at the full population, mean 100%, all of the data. Okay, and we've seen before what a normal distribution is. It's symmetrical left and right, and you'll find the peak or the mean, showed by this red line, is in the center. Okay, we've seen skewed distributions where the mean might be, in this case, to the right, okay, of the peak, and that's due to these large outliers or this tail on the right hand side. Uniform means it's the same the whole way across, and our mean is here in the center, and here at the end is a completely irregular distribution with a mean there. Okay, now let's see what happens when you take samples. So the first row here says n equals 3. So what produces these graphs are lots and lots and lots of groups of 3 picked at random from the original set of data. Okay, so they've groups of 3 numbers, and then the mean of those 3 numbers is calculated, and then all the results from all the samples. So there's many of these n equal 3 samples, and all of the means from all of the samples are put into a histogram, and what you will see is that the mean of all of those samples, so all the sample means, will be the same as the mean of the original population. Okay, notice also the shape of this. Okay, it produces a normal distribution. Okay, so this is normal as well, okay, to the right and to the left. Also though, let's go to what was our skewed population. What you'll notice with all the sample means is that your sample distribution is not skewed. Your sample distribution is normal, or more or less, okay? And the mean will agree with the mean of the population. The same goes, look, here's a good example of the uniform distribution initially. Okay, when the samples are taken, the sample distribution turns out normal, but the mean agrees with the original population mean, and the same here you can see there with the irregular distribution. Okay. Now what happens when the samples taken are bigger? So you take many samples of size 5. Okay, and with those 5 groups of 5, the mean of each group of 5 is calculated and put onto a histogram, and again the mean of the samples will agree with the mean of the population. Okay, so we can see that. But you will also observe that your sample distributions are looking more and more normal, and they are also getting thinner, okay, or narrower. You can see that more clearly with n equals 10 and n equals 20. So if you take many samples of size 20, the mean agrees with the population mean, but the spread of that distribution is much narrower. Okay, and the same is seen across the whole way. Okay, and that's what we said above. The mean of the sampling distribution is the same as the mean of the population, and the standard deviation, or that measure of spread of the sampling distribution, reduces, gets smaller as the size of the samples taken are increased. That brings us to the central limit theorem. If a sample is large enough, n is greater or equal to 30, the sample means will have a distribution that is a normal distribution about the population mean mu. Okay, so we've seen that on the previous slide in those pictures. Okay, regardless of the shape of the original distribution, if you have enough in your sample and take enough samples, then they will make a normal distribution. Okay, we can say, so some notation here. This here, mu, generally we say mu, it's a Greek letter. Okay, here we have mu of x bar, so this is the mean of the sample means, so lots of means going on. So if you calculate all the x bars, okay, from all your samples, then mu x bar is the mean of all of those, and plain mu is the population mean. Okay, and the sample means will have a standard deviation of, so again, similar notation, this is the standard deviation of, so standard deviation of sample means, okay, is given by sigma x bar is equal to sigma, which is the standard deviation of the population, divided by the square root of n, where n is the sample size. Okay, so you can see also as n increases, as the sample size increases, okay, it's a denominator, it's dividing. As that number gets bigger and bigger, then the sigma x bar, that standard deviation, decreases. Okay, so and that is the central limit theorem. Okay, and we'll see how it's used in questions shortly. It's used in combination with probabilities and z-scores. So z-scores for sample means. Given a sample mean, we can use z-scores to infer probabilities about the sample distribution. So we're looking at the probabilities about the sample. Okay, first we need to calculate the z-score of the sample mean. Okay, and this is different to when we were working with the full population. Okay, this z-score formula is given by the formula below, which is on page 35 of your formula and tables book. That's what it looks like, and it's called a one sample z-test. Okay, so there you have z is equal to x bar, which is the sample mean, minus mu, which is the population mean, divided by sigma, which is the standard deviation of the population, over the square root of n, where n is the sample size. Okay, and we best put that into practice to make sense of it. So here's an example. Women's heights in Ireland are normally distributed with a mean given by mu equals 16 or 164.4 centimeters and a standard deviation given by sigma equals 6.25 centimeters. Okay, so that's a normal distribution. If a woman is selected at random, find the probability that her height is less than 167 centimeters. So this is a woman selected random from the full population. So we're doing our original z-score calculation. We're working with the full population. So we'll use the regular z-score formula, which is x minus mu over sigma. Okay, so write down that formula for your examiner. Yes, we're doing probabilities, so whenever probability is mentioned with things like mean and sigma, you're talking z-scores. Okay, so calculate your z-score. So the x will be 167 centimeters, so that's the value we're given in the question. Okay, the woman's height. So okay, minus mu, which is the mean of the population, 164.4, and we'll divide that by the standard deviations. Okay, and when you work that out, I got 0.416. Now, in the formula and tables book that you are using, we only get z-scores to 2 decimal places, so I'll round that up to 0.42. Okay, so now let's go find that in the z tables, 0.42. So we're working with the first page of z-scores, and here is 0.4. We need 0.42, okay, in the second decimal place, and so I get a result here of 0.6628. So what we found out was that the probability of getting a z-score that is less than or equal to 0.42 was equal to 0.6628, or 66.28%. That says, translate that then back to heights, it says that 66.28% of women are less than 167 centimeters tall. Okay, so the next part of that question, so the same stats, the next part asks, a simple random sample of 25 women is selected. Find the probability that the mean height of the sample is less than 167 centimeters. Okay, so now we're asked to draw conclusions about the sample. Okay, so not the population. So again, probability is mentioned. So we're going to be talking z-scores, and for a sample, the z-score is given by our alternative formula for a one sample test. Okay, and we'll go through these figures now in a minute. So this is the z-score for a sample. Now, so let's go through the question and get the information. So the first figure we come across is 25 women, so n is equal to 25. Okay, we know from the original information that mu is 164.4, sigma is 6.25, and what do we also have? We also have the sample figure. They're asking us to test about 167, so we'll use that as our x bar. Okay, sigma and n is 25. Okay, all right, so now let's substitute into the formula. So we have 167 minus 164.4, all to be divided by 6.25 over root 25. Okay, so let your calculator do the work, and you get a z-score of 2.08. Okay, so we'll be looking for what's the probability that we get a z-score of less than or equal to 2.08. So we need to go to our z-tables again. So here we're on the second page of z-scores, and their probabilities, and we're looking for 2.08. So along the left we get 2.0 is here, and in the second decimal place we need the digit 8, so which is over here. That will give us 2.08. So scrolling down where those two concur, and we get 0.9812. So the result we got was 0.9812, or 98.12%. So it says that the chances of the sample mean being smaller than 167 centimeters is very high, 98.12%. Okay, now part 3 of that same question, which is very interesting, asks you to explain why you were able to use the central limit theorem in part 2 even though the sample size does not exceed 30. So we only had 25 in the sample size. Okay, now the reason for this is that the heights of the population of women in Ireland is normally distributed. So for samples smaller than 30, you can use the central limit theorem if the population is normally distributed. You can't use it for, say, a skewed population or one of the other populations, okay? But you can use it for a normal distribution. Now here's an exam question that uses the central limit theory. Okay, so let's read it. It's from 2018. It's question 8, paper 2. Acme Confectionery makes cakes and chocolate bars. So the first part of the question was, Acme Confectionery has launched a new bar called Chocolate Crunch. The weights of these bars are normally distributed with a mean of 4.64 grams and a standard deviation of 0.12 grams. A sample of 10 bars is selected at random and the mean weight of the sample is found. Find the probability that the mean weight of the sample is between 4.6 and 4.7 grams. Okay, so lots to take in there. Okay, so they're talking about means and standard deviations with the word probability, so we're talking z-scores. We're talking about a sample. Okay, find the mean weight of the sample is between these values. So we're talking about the z-score for samples, which is, we'll write down the formula there for when we need it. Okay, from your formula books. Okay, again, similar to the previous question, a very small sample here, but because the weights of the bars we're told are normally distributed, we can use our central limit theorem and we can work away here. Okay, so firstly it's useful to make a list of your values and what you have. So the mean of the population, which is mu, is 4.64. Okay, standard deviation from the question is 0.12, that's of the population. Our sample size is 10. And we're going to work with two different sample means. We're going to get a z-score for 4.6 and we're going to get a z-score for 4.7. Okay, and we'll use those z-scores to work out the probabilities. So we'll call it Z1. Okay, for the first one will be 4.6 minus 4.64 divided by 0.12 over the square root of 10. And let your calculator do that work and you get minus 1.05. Okay, and then for the second z-score we'll use 4.7 and everything else will remain the same. Whoops, and I get 1.58. Now let's read the question again. Find the probability that the mean weight of the sample is between 4.6 and 4.7 grams. So let's visually see what we're talking about. Okay, so we have a normal distribution. Okay, what's the probability that the mean of the sample is between a z-score of 1.58 and a z-score of minus 1.05? So we're looking for the probability, or this proportion here that's shaded. Okay, so we've worked with z-scores before, and we're going to have to do some thinking around this, because the z-scores only give probability to the left. Okay, so how will we get this shaded portion? That's an 8. So it's easy enough for the 1.58. We'll start off by getting the z-score of 1.58, and we will be subtracting the proportion that is, we would like to subtract the proportion that is below minus 1.05. Okay, now we know that we don't have a table for negative z-scores, so we know that we can replace this with the proportion of the graph that is greater than plus 1.05, so this little tail end here. But how do we calculate that? Well, we will do 1, which represents the full distribution, minus the probability of a z-score less than 1 plus 1.05. Okay, so we don't use that any longer either up there. Okay, so we're going to go for the probability that z is less than or equal 1.58 minus 1 minus the probability that the z-score is less than or equal to 1.05. Okay, so keep those two figures in your head, 1.58 and 1.05, and we'll go to our z tables. Okay, so 1.58. Okay, so we're on the second page of the z-scores, and 1.5 is here, and second decimal place 8 is over here. 1.58, and we get 0.9429. Okay, we'll use that in a moment. 0.9429. So that's the first one we needed. And the next one was 1.05. Okay, so we have to go back to the first page of the z tables. 1.0 is here at the bottom, and 1.05 we'll get if we add this in the second decimal place, and it's here, so 0.8531. So bringing those figures that we got in here. Okay, so the probability that we had a z-score less than 1.58 was 0.9429. Subtract 1 minus, for the second one, 1.05, we got 0.8531. And when your calculator figures that out, well, let's do the bracket first. Minus 0.1469, we get 0.796. Now that's the probability that our z-scores lie between minus 1.05, that's our z-scores, lies between that and plus 1.58. But that also gives us the probability that the mean weight of the sample is between 4.6 and 4.7 grams. Okay, now out of interest, on the next slide I have the marking scheme for that part of the question. And you see that there are 20 marks going for that first part of part A. Okay, so 20 marks, good chunk of it. All right, so here we see our z-scores, which we calculated correctly. All right, and our probabilities that we got from our tables correctly, and our 0.796. Okay, notice that there are opportunities to gain partial marks, 5, 10 or 15. Okay, so 5 would be known as a low partial credit, and you'd get 5 if you had a go at calculating the Z score. Okay, Z1 formulated, so use the formula and you put in some correct values when you're substituting. Okay, or if you got some of Z2 right. A mid partial credit, so 10 out of 20, will be if you get Z1 and Z2 fully substituted. Okay, and high partial credit, so you get 15 out of 20 if you got the Z scores right. Okay, that's without going to get the probabilities. So lots of marks on offer there. Have a go and see how you get on.